All right, we're going to kick this thing off. Welcome to the Hitchhiker's Guide to the Cosmos DB. Just out of curiosity, before I get started, does anyone here know why I have a towel right now? No. Show of hands. Okay, so there's a couple diehard Hitchhikers fans. For those of you who are not big fans, it's the most massively useful thing an interstellar hitchhiker can have. But there's no worries if you are not familiar with Hitchhiker's Guide. That's not what our focus is. It's definitely Cosmos DB. Is anyone working with Cosmos DB right now? Saw a few show of hands. What about other NoSQL databases? Not so much. All right, good. Well, we're going to cover a lot of ground then. Start out with just a little bit about myself. I know we only have 50 minutes, so I cut this down to 30 so we could jump into the good content. I'm a cloud developer advocate with Microsoft. I'll talk a little bit about that in a second, but the main point of this slide is that I've been professionally developing for a really long time. It's a quarter century if you don't want to do the math, and I've been doing it as a hobby before then. This is my contact information. I have a blog that covers cloud development topics. My Twitter direct messages are open, so feel free to follow me, but you can DM me if you want to give me feedback, and that's how to get in touch with me. I'm part of a larger team. We're a global team around the world, and we focus on different technology areas at Microsoft, and I get a lot of questions about what we do, and I distill it down to 3 key points. We work with community and go out to where developers are, whether it's in person or online. We work with content. We're very closely aligned with the docs team. I have a link to the Cosmos DB docs, and we want those to be the best docs possible for developers to get online. And the last thing we do is we connect with engineering. We don't report to marketing, we report to engineering teams. And so my job is when you're going out and trying these things or building solutions, if you have challenges, I'm the person you can reach out to and who can help out with those and work with the teams back at Microsoft to improve the product. So I do encourage you to reach out to me after this. What I'm going to cover today is a little bit of legacy. We've all probably worked with SQL for quite some time. There's some of you who may not be familiar with NoSQL and what that concept is, so I want to cover that. And then Azure Cosmos DB is the fully managed solution that we have. I'm going to go into those features, and we're going to do a lot of demos. And it is the cloud, so demos are online, so we'll cross our fingers about the internet, but I do have backup plans for that. So has anyone run into this in any of your jobs? Why are you doing it this way? It's because we've always done it. Anyone heard that before? Not heard it? So this is something that I'm on a mission to dispel a little bit because there's a long legacy with SQL as the database. Now I would be selling the story short if I said that the only reason relational databases existed was because of storage. But that was a big part of the story. When relational databases came out, storage was exponentially more expensive. We had a great kind of walk through history with the keynote this morning, but the main goal was to normalize as much as possible so we weren't repeating information. And that's been a huge driver to these concepts of databases. And I just want to point out for those of you who are fans of the Hitchhiker's Guide to the Galaxy, that's 4 and 2 makes 42. Okay. So this focus on relational databases has created this interesting dichotomy. We have DBAs who are experts at how the database works, and they know how to express data relationally. And then we have developers who work with domain-driven or test-driven or object-oriented development. And this creates a little bit of a disconnect in our data, and we need something in the middle. Does anyone know what that is? ORM, right. So that's what we're missing is this ORM in the middle. And I'm not here to tell you ORMs are a bad thing. There's some very successful projects that run off ORMs. Some of you may have been on that project where you either had to change a property or add a property, and you had to get it approved by the data team, have the data team build a schema update, roll out a schema update, you added the property to your class, you updated a bunch of unit tests, and then on top of all that, you had to go to the ORM and tell the ORM that you added a new field. Anyone run into that any period of time? Maybe a few of you. So this can create a lot of overhead and ceremony. And just, by the way, I want to keep my focus on my Hitchhiker's Guide fan. If this was gold and wrapped in a lemon, it would be a pan-galactic gargle blaster. So if anyone's not familiar with that, it's something to look up. So another thing that I've seen in the history of SQL is this metadata table, right? We always end up with a table that has column names that describe column names and data that describes data. And the whole reason is we want to cheat this need to roll out schema changes. So we want to have volatile data that changes from one set to another and not have to constantly update our database to store it. So we do have some unique solutions for that, like stuffing it into an mvarchar max. I'm sure you've never seen that in code, but some people have done it, not here at DevReach. And then there are actually native XML and JSON types that give indexing and do that. But I'm going to just postulate that if this is how you're using your SQL database, you're probably missing out on some tools that we have available. And that's NoSQL. And I think a lot of us can get turned off by NoSQL in the beginning because we feel like SQL's not allowed. But it's really become this idea of not only SQL. So there's other tools for the job. And there are dozens of flavors of NoSQL database. These are 4 of the very common flavors: key value, column, document, and graph. If we look at key value, this is really a persistent dictionary. And this is a perfect way to do a couple things, and I'll give you 2 very specific examples. One would be a user profile that your data about the user may change over time, but you always know the ID of the user when they log in. So this is a quick lookup, right? You take the user ID, you look up the table, you get the value. You're not indexing by properties on the user, you're getting information about them. The example that you see here is a link shortener, which we'll dive into a little bit more, and it's simply mapping a short link to a long link. So that's a great use of key value store. Document we'll get into, that's literally what it means. We take a class as a set of properties, we call it a document, we store it. We can have richer data than this, and we'll see those examples in a minute. Then we have a graph database. Graphs express relationships. We have nodes or vertices, and those can have different pieces of information. And then we have edges that point between nodes and vertices. This is a canonical example of airports that have flights between airports. Another great example might be a family tree. So my node would be a person, and then my edge would be a relationship with the person. And those edges can have information associated with them as well. They're just a special type of document. And then we have column database, which takes what we would normally express and think about in rows and materializes it as columns in the database. That's how it's physically storing it on the back end. This gives us 2 advantages when we use this approach. The first is that if obviously we're doing searches and indexing by columns, we have a highly efficient lookup. But more importantly, if we're projecting data, so if we have a very large amount of data, but we're only pulling back a few properties, the way this is organized makes it highly efficient to pull back just what we need from that query. So having said that, all of these flavors of NoSQL are handled by Cosmos DB. I'm going to jump into some examples of it. First thing I want to do is create a database. Anyone here set up a SQL database? Out of curiosity. Your hands are going to get tired eventually, I know, but what about a SQL cluster? Oh, not so many hands. We let the database people do the cluster. And then there's also a geo-replicated cluster, which I've participated in. I'm not knowledgeable enough to do that myself, but I've seen the pain they go through. So one of the nice things about creating a database in the cloud, and this goes for Cosmos DB as well as if you have SQL or PostgreSQL, or I think I pronounced that correctly, or MySQL. When you go into the cloud, setting up becomes a lot easier because whoever's managing that cloud for you is handling that scale out and that replication. So in this case, I'm coming in, I'm creating a new database, I give it a subscription because they need to know where to send the bill. I give it a resource group. This is just a container for related items. And I give it a unique name. So we could call this something like DevReach. So you want to have a DevReach Cosmos data? They don't yet. So that green check mark means that name's not taken. I can pick an API. I'm going to talk a little bit more about what that freedom gives me in a second. I can pick a location, and I'm just going to leave the default because I'm not actually going to create this database. I obviously probably may or may not use Australia for this example. But this is pretty cool here if we hover over our geo redundancy. To have geo-replication, I click this button and then I click create, and it's a done deal. And we're off to the races. So it's pretty powerful to get that kicked off, and it takes anywhere from a couple minutes to several more than a couple minutes to provision that resource, so I'll spare you that time. But I wanted to cover a few reasons why I would even want to go through that much effort to create that database. And these are advantages of looking at NoSQL databases from the ground up. Every document's independent. That means if I change information, I don't have to update a schema and go back and update previous records. I just add it to the database. It's incredibly flexible. But that doesn't mean it doesn't support indexing. Everything's automatically indexed for me, and I still have fast lookups. In fact, these are designed to be incredibly fast databases. It's easy to manipulate because I'm just dealing with my object model, and I call it JSON ready. Most of the NoSQL interfaces will return JSON out of the box. So that means I'm not going from a data set to a class that's then turned into a data adapter that's then serialized to JSON that's then brought to the browser. I can take that information directly and transform it into actionable data. We're designed to manage data sets that are terabytes to petabytes in size. That's what we mean by large data sets. And version proof is perhaps my favorite thing. If we have a new version of the table, we start writing out the new version. We don't have to go through this ceremony and ritual of change. It's ORM free if you want it to be. Most of the drivers will take your classes directly and serialize them to the database. But if you're, for example, building a strategy based on Entity Framework, there is an adapter for Cosmos DB coming out for Entity Framework, so you're definitely not isolated for that. One of the benefits when I check that box with the geo-replication is it's turnkey. And what that means is I give Cosmos DB a little hint about what makes data important to be held together. So if you're doing a multi-tenant system, for example, you might want a customer's data to be closer together. Cosmos DB will take that and automatically optimize where it's going to be physically stored on disk, and it uses these units called partitions that it can easily replicate across regions. And it will do that all for you. You don't have to worry about what is my partition strategy, what is my sharding strategy. We get elastic scale out. Cosmos DB is a really unique model. Unlike other models that are reactive, so as your demand grows, then it may react and there may be an adjustment period. The way Cosmos DB works is it provisions a cluster to meet a guarantee. So if you know you're going to have high throughput, you pay up front for high throughput, and it will guarantee that throughput by provisioning the right amount. I'm going to go into that in a little more detail because there is more flexibility there than how that sounds. But you basically pick it. There's another pretty cool feature. A lot of people miss out on this feature, and this is automatic document expiration. I've talked to several people who have jobs that are periodically polling the database and deleting old records. And in Cosmos DB, you can just tag a record, give it a time to live, and it'll purge itself automatically. Saves you a bunch of service jobs that are constantly pinging it. Now we're going to talk about low latency and how we have sub 10 millisecond reads, so that's a pretty fast read time. You can see there's a little bit of variety here based on a consistency model. So before I just gloss over that, I want to talk about consistency models. Who here is familiar with consistency models, by the way, just out of curiosity? A few half hands. So this is probably one of the tougher ideas to grok when you go to specifically Cosmos DB. It's some NoSQL database, but Cosmos DB. We have these different consistency models, and it's all based on CAP theorem, which is a way of looking at, we're just going to cancel out this creation. It's a way of looking at distributed systems, and it basically says we have consistency, availability, and something called partition tolerance. Partition tolerance talks about what I know we've never run into before, but some people with other systems experience, and that's actually what we're looking at right now as I wait for this to come up. And I do have a backup in a second, and that's sometimes the network isn't reliable, right? So that's your partition tolerance. So how do you compensate for that? What are the ways you can deal with that? Okay, we got something going here. So what Cosmos DB does is it lets you pick how you want to compensate for that. So what most people are used to is something called strong consistency. That means wherever I write, East US, West US, Australia, anyone who reads is going to see the same thing, which sounds really good until you look at the mechanisms that make that guaranteed. This means that every time I add something to the system, every single copy all over the world over the reliable internet has to be in agreement that that commitment was made so that it has that consistent result back. So this makes this the most expensive model that has the lowest availability, because if anything goes down during that time, you have to wait till it comes back up so it can propagate. So it's a very efficient model. So the way we deal with that is we have these different levels. So there's a compromise called bounded staleness. What bounded staleness says is, you know what? When I read, it's okay if I read a little bit of an older copy. So it's okay if I write these musical notes in the East US, but when I read them back, there may be a delay for it to propagate, and I can set a time period. And so it's a little bit of a compromise. It still requires a guarantee that something matches at a point in time, but it gives all the replicas a little bit of time to catch up. What's weird about this is, let's say you're building a nutrition program, and it's a social program so your friends can come in and read it and like it. You might update a meal and then refresh to see your calories, and your meal's not there yet. That would be a really odd experience, right? It's not how we want our software to work. So there's a compromise called session consistency. And the way session consistency works is, within a particular session, the reads are guaranteed to match the writes. But outside of that, there's going to be a little bit of a delay. So that means in my social networking site, I will update and refresh, and I'll see a consistent experience. My friends may not see that update for a period of delay, and then they can like it and say, good job, or where did you get that beer at, that type of thing. So it's a compromise for the system. Then we have something called consistent prefix. And by the way, starting at the session level, you're looking at about half the cost of the bounded staleness and strong consistency, because you're giving more flexibility to the system to propagate information. So if we talk about consistent prefix, this is really the same thing as bounded staleness. There's just no time guarantee. You're saying everything needs to be in order. So if I'm playing a song, my notes need to come in order, but it can come in at any time. If it takes 10 minutes to make it across the world, then it takes 10 minutes. You may have a system, for example, that has a high volume of users who are commenting on products, and so it doesn't really matter if that's instantaneous. It's okay if it eventually appears in other regions, and so you can use this. And finally, the last one, which is probably the most confusing to people who work on relational database, is eventual consistency. That means whatever, eventually we'll catch up. So basically, and I'm not going to try to sing because I'm completely tone deaf, but my song that's brilliant in the East US at the top, you can see these other notes are coming in out of order. So that seems a little odd. This is the highest available, lowest cost way to synchronize. And you may ask, well, why would I even do this? Well, it's not going to make sense if you're tracking sports scores. But let's say you have 1 million devices that you have sensors attached to, and you're taking readings from those devices, and what you're concerned about is information in aggregate. Well, using this model ensures that you have rapid writes wherever those writes are going in. Your trends are going to be, on average, normalized across the board, so you're going to still see what's trending. You're just not drilling into a specific device and expecting it to come in really precise order. So that, I don't want to spend too much time on that, but that's consistency levels. Just out of curiosity, did anyone walk in not understanding these, and hopefully will walk out with a little bit better understanding? Show of hands. Or have I failed you? Oh, this is awesome. Thank you so much. It's like we planned it that way. So I talked about interfaces when I created the database. Cosmos DB supports right now 5 interfaces, and there may be new ones in the future. And there's 2 reasons why we do this. Some of these interfaces are proprietary. The table API was introduced with storage, and that's the key value store. The SQL API is actually for a document database. It's not a structured relational database, but it lets you use your existing knowledge of SQL to query the database. So it allows you to leverage existing skills. And this is the reason why we have some of the other APIs. When we're doing a graph database, there's a very popular API called Gremlin that's supported in the field. It wasn't invented at Microsoft. But by supporting it, it makes it easier to port applications into Cosmos DB. It also enables existing tools. And it's really cool. Gremlin's a cool name anyway, right? And then there's a tool called Tinkerpop, and there's just all these awesome names that we're just not as creative as naming them locally. So speaking of interfaces, I want to jump into our first example of a link shortener. So I have a twofold challenge. The first is I want to take long links, have a short URL to link to them. So that's a very good opportunity for a key value store. Second thing I want to do is when people use links, I want to build information about them, gain data and metrics that I can aggregate and look into. So let's jump into first example of a database I've created, and this is a table database. And if we zoom in here, you can see that it's calling them tables. I have one called URLs, and I can drill into URLs. And then we'll see our little spots. And everyone knows this trick, right? If you're ever stuck with a slow internet, you just move the mouse clockwise, and it speeds things up. So we go into our URLs. And again, we're going to use this trick. See, it works every time, guaranteed. And what we have is two entries right here. We'll collapse this. So I have a key that has this hard-coded ID value. I'll zoom in so you can see that better. So it has this hard-coded ID value. Then we have this other entry that has this AAA. It's mapping to a URL, and it has a count. So what I'm showing you there is we have this unique key across the database, but the data that's in each entry can be fundamentally different. If we would look at the code that gets us there, I've got basically this entity that I'm using the SDK. And what's interesting to me is an ID, because I'm doing my next up code 1, 2, 3, 4, 5. And I inherit from this table entity class that has these base properties like the global key that I'm using. So I'm not looking this record up by ID, I'm looking up by the hard-coded value key and saying, what is my next short code that I'm going to use? Then if we take a look at another entity I've defined, this is my data. What's interesting to me about this one is that I get a URL and I keep a really light count of what's going on with that URL. So now if we look at code, we'll jump into here. Now this happens to be using serverless functions. Main reason I use it's an easier example, but it's also because I'm talking about serverless tomorrow. So if you want to learn more about this, it's a free advertisement that I was able to inject into the talk. But in all reality, what we've defined here is we're using something called a binding that lets me just slap an attribute on a property, and the SDK is going to do everything for me. So I've got a default connection string. I can override it to another connection string if I want to. In this first example, I'm telling it, give me that hard-coded key value. And it's going to grab it and pass it in. There's no create this class, pull in a connection string, open the connection, look up the table, grab all that. Forget that. I can just put it in a set of attributes and pull it in. This one is a more generic operator that lets me interface with the table. So I'm pulling a URL from the call. I'm looking at, do I have that next up seed value? If not, I'm going ahead and inserting it. So again, this should not be scary code for anyone who's worked with C# at all. And the interfaces, by the way, for JavaScript on Node or Python or other interfaces we support are very similar and straightforward. I basically build up my entity and then I insert it. That's all I'm doing. This is just an algorithm that turns numbers into letters because they're cooler to look at for short URLs. Then I'm packaging up my URL with a count and I'm inserting it into the table. So pretty straightforward API. Then on the flip side of that, I may want to go ahead and take that short URL and redirect it to a long one. So this code is, again, pulling in that URLs table. What we're doing here is first I'm priming it, because if I get a bad short code, everything should end up at my blog, right? And this is pretty important. We even burned out a light talking about it, apparently. But everything defaults to the blog. However, if I do have that entry in the database, I'm going to grab that entry, and then I'm adding something to a queue, which I'll talk about in a second, and then I redirect. So again, pretty straightforward code. I use this retrieve operation. I'm retrieving URL data. I'm passing it the key, and I'm grabbing it. Now, the reason why I throw the key on a queue is because I mentioned the other part of the problem I want to solve is analyzing data. I don't want the user to wait for me to do stuff with data. I want to redirect them as quickly as possible, because if someone clicks on a link and waits 10 seconds, they're gone. They're somewhere else. So I'm going to throw this on a queue, use some other process to pick it up and do something interesting with it, and we'll go from there. So in this example, that other process is pretty straightforward. Again, I'm looking up a code. I'm incrementing the count. I'm replacing it with the count and running this. So with the power of local emulation, what I can do is kick this off. And one thing you'll learn if you come to the serverless session tomorrow is the serverless host is a cross-platform host that'll run the full serverless experience on your laptop. So I'm able to just launch this program locally, use a local emulator, and go through all my debug and testing cycles. I don't have to have something wired up to the cloud for this to work. So what this is going to do is jump in, inspect my code, and it's going to find out, what serverless functions have I defined. And then we'll speed it up a little bit here. And it generated 3. So it's giving me the local URLs that I can use, and I have a go and a set. So let's go ahead and take this set. I just want to make sure I copied it so I don't have to come back. Okay. And then I'm going to jump over to my Storage Explorer and show you that in these tables here, I have some of these weird backend tables, but there's no table called URLs. That's not created yet. If we go back into our web browser, and I'm going to do set, and let's just go ahead and pick a interesting href. I tend to be pretty creative about these things, so I'm going to use DevReach.com. And it's going to spin out. It's going to hit that function app. It's going to look for a first up seed value. If it's not there, it'll set it up. And you can see I got this BP value back as the response. So what we can do now is we can jump back over to our Storage Explorer, and we can issue a refresh. And the URLs table is created for us. And I have my key seated to the value of 42, which is a very important number. And I have my BP pointing to DevReach. And I went ahead and initialized it with a count of 1. It should probably start out as 0, but that's okay. You can see it's 1 here. So what we'll do is we'll come back and we'll do a go and use the shortcode it gave us, which was BP. And if everything goes well, the internet's happy, cooperating with us, we end up on the DevReach homepage. So pretty straightforward. And then if I come back over and I look at my storage and I refresh that, you can see my count went up now to 2. So pretty simple metrics. Now I've got a full production version. That's the easy version that I can walk through in a demo. What I actually run is also open source. And it's very similar, but let me stop this from running so I don't have any unexpected side effects. It's very similar, but in my process, instead of just updating it on the table, I store it as a document in a document-based database. I'm using the SQL API. So in here, I've used another attribute that's saying, and this is updated, by the way. I need to update my code base. It's now called Cosmos DB, so it's less confusing. But I'm giving it the name of the database, the name of the table, create if it doesn't exist, and it's passing in just a dynamic variable. So I create an expando object because in the NoSQL world, I don't have to set 500 properties to null. If you look at my logic, as I'm building this up, if I have a short URL here, I'll add the property. Otherwise, I don't even bother adding it. I don't need to. It's just overhead because I'm in a NoSQL database. So this is a lot of code building it up, And what's nice about the serverless app is when it returns, it simply inserts the document for me. I don't have to write any extra code. It's just done for me. So if we come back over to my database here, first thing I want you to notice is that this is now called a collection, not a table, because I'm dealing with a document, not key value pair. Still Cosmos DB, but I told it to use the SQL API. I've got some redundancy East and West US set up. And if I go into this table, zoom back out so we have some context, this is going to give me a list of entities. And what we'll see here is when I click on documents, it's going to pull back some IDs, and we can see here's a sample document. Now this document was when I first started collecting information. I had the page, I had a count, a timestamp, and this particular one came from a presentation link. Pretty simple. I've gotten a little more in-depth with the data I collect over time. So let's do this. Let's write a query. And you can see this is SQL syntax, so if you're a SQL developer, you're already familiar with this. I'm going to change this to select top 5 star from C, order by C, timestamp descending. So I want the 5 most recent documents that probably happened while I was giving this talk. So if we execute that query, you can see that these documents come back and they have a little bit more data. They have a short URL, campaign, a host that's normalized off of where it's sending to. So someone's interested in static data masking, which is a recent article release we had. So a little bit richer data from that. Now what's interesting about this is even though I have different documents with different pieces of data, that doesn't prevent me from running analytics over it. So this is a live Power BI dashboard I use to look at what links are popular links. So this week, Azure Event Hubs for Apache Kafka is a pretty popular topic. I can look at what channels are generating links. Twitter by far is my most active channel. I've got LinkedIn and a blog. I can look at what day of week are more people clicking through links, so that's useful information. Can come across the board, look at page views over time. So this is kind of the flow over the month, and you can tell sometimes when I travel, I'm not creating as many links. I have a campaign matrix, so what campaigns are. And what's interesting too is I have this refer, and one of the enhancements I made was I backtracked the link to see did it come from a tweet, and if it did, what was the tweet? So now I can, so hopefully all of my tweets are presentable in public, so I'm just going to blindly click on that and see what the most popular tweet this week is. And this is busting myths about working remotely. So that was the most clicked on tweet that I did this week. So you can see I can do tons of analytics right off of the document database. Now having said that, I showed you 2 different types of database. I showed you a table key value store, and I showed you a document with the SQL API. I'm often asked, well, are these completely different instances of Cosmos? And the reality is Cosmos uses something internally called Atom Record Sequence. So internally, it's storing what it calls primitives, which is going to be like a URL, a date, a number, a string. And then it has either records, which are groups of primitives together, or sequences, which can be arrays of atoms, groups, or other sequences. So it's a recursive internal data model. And then what it does is it projects that onto the API. So I have this concept called a container, which is where I would put things like stored procedures, user-defined functions, triggers, so it's related documents, and then it's going to project it. And if it's MongoDB, it uses collections. If it's table, it's going to use tables. If it's Gremlin, it's going to use graphs. So it projects that on top of the internal data storage. And the same token for the individual items, if I'm on MongoDB, we call them a document. If I'm in table storage, I have a key and a value, which is a document. And if I'm in my graph database, I can have a vertex or a node, and I can have an edge with information about it. So that's how it handles those different amounts of APIs. So all of this comes with SLAs that I don't have to worry about, meaning we talked about 10 millisecond. there's high availability, guaranteed throughput. I'm going to dive into that in a second. And then consistency. So those consistency models I talked to you about, they're basically guarantee that if you set up strong consistency, you're not going to get eventual consistency, which would be really confusing and weird and not a pleasant experience. So I talked about how you pay up front for what you want to do, and then Cosmos makes it happen. So this uses something called a request unit. A request unit is just the amount of CPU, memory, and disk it's required to complete something in Cosmos DB. So you can imagine getting something off disk is a really lightweight operation as far as CPU and access is concerned. Putting something or replacing a record is a little more expensive, so it's going to take a few more request units. And then queries could be all over the board depending on how complex they are. And then what you do is you establish request units. Now, fortunately, there's a tool that's linked to in this deck that lets you update sample documents, and it'll help project what request units you need. On top of that, you can override request units at your connection. So if I'm building a tool that's importing a high volume of data, I may want that to have a higher set of request units configured than if I'm doing normal day-to-day operations. So I have a default that's set at the collection or database level, and then I can override that. And then if I exceed it, I also get a message back that gives me information about how long do I need to wait so that I can issue that request again, and what would I have needed for that request to be satisfied so I can tweak what my levels are. And that's the part of this where I'd like to say it's as easy as clicking a few buttons in the portal and you're in production, but there is some work involved with tweaking and getting it optimized based on your workloads. Now, I showed you two of the interfaces. I showed you the table and the SQL. I want to show you MongoDB. It's a very popular database, been around a long time. Anyone developed to MongoDB here in the audience? So a few shows of hands. So we'll step through this. So what I used was the USDA database. This is a relational database, has 12 tables, and it's information about food. So this food has these nutrients in it, and it's measured this way. I use cups, or I use teaspoons or tablespoons, and it has this many calories, this many carbohydrates, this much fat, etc. What I've done is created a program you can download. It's open source. It'll take those tables, import them into 3 collections in the MongoDB API of Cosmos DB. There are food groups, nutrient groups, and food items. Now, the reason why I chose 3 is because it's really easy for me to have just a list of food groups and grab them. In fact, that could have even been a separate key value store table if I wanted it to be. That's just ease of use for the API. The main data, which is the food items, goes in that one collection. Now, if you're doing a relational database, you'd have this food item, and then you'd have this nutrient, and then you'd have another key that said for this food item and this nutrient, it has this value. But with this approach, we can have all that stored in the same document, and it's perfectly fine. Now, one of the nuances about it, I talked about indexing still happens, even if documents are different. We tend to approach code thinking of things that can be variable as arrays. So I may have one food item that only has one piece of nutrient information. I may have another that has a dozen. And so as a developer, I may want to express that as an array because it can have one-day in items. What's nice, though, is in NoSQL, it's fine to have those as properties because I can have one document that just has 2 properties, one document that has 5 properties. And if I do it this way instead of the array, then I'm automatically indexing over those properties so I can do fast lookups, and I'm going to show you a demo of what that looks like. So let's jump into this. The first thing I'm going to do is explore the database, and to avoid having the internet interfere with us too much, I'm going to jump into this example. This is one I've practiced so much I can do it without my hands, so it's really cool. So I'm going into the database, and you can see here it's collections, because MongoDB uses collections just like the SQL API, and I've got redundancy east and west. I'm going to drill into the food items portion of the database, and similar to what you saw before, I can drill into documents, only now you see 2 properties for this. This is because I've defined a partition key. I'm going to allow it to shard and partition my data. And all I did was when I defined the database, I said use this property as a partition key. Obviously, that means that property is now required on every document. It's the only requirement that I have. You can see I have structured data. It's nested inside. I've got nutrient information, protein, carbs. And then what I can do is use the MongoDB style of querying to query the database. Now, in MongoDB, you query by writing JSON, which took me a while to get used to, but it actually makes sense once you use it. So what I'm querying in this case is I'm saying there's a property called description, and the way I want to query it is I want you to run a regex on it, because we all love regexes. I've done a really simple one, though. I'm just looking for the word scrambled, and I'll run it. Now, this one is looking inside the text for scrambled. So it's going to have to scan every record in the database to find that. So I get 3 documents back. I'm showing those documents in the results window. But what's nice is when I'm doing this in the portal, I get stats back on how many request units. So this case, it took 3,300 request units, rounded up, to execute that. So we can do a little bit better. I'm going to take advantage of the automatic indexes, and I know 2 out of 3 of my scrambled egg documents are in this dairy and egg products group. So I grab that dairy and egg products group, and I'm going to do an and, which just says these are all the conditions that apply for the query. So I pass it an array of conditions, and this is, again, the Mongo syntax. So right now there's and with just one object that says find the description. I'm going to add to that, and I'm going to say, and I want the group.description so I can navigate down properties to equal dairy and egg products. So I'm just saying look straight at the index and pull this back. So I'll execute that. I get 2 documents because one of them was in a different food group. But because I'm using the index, now we're down to 175 request units, which is a pretty big improvement. So it's the importance of having a partitioning strategy coming into play. I can do even better, though. I did not specify group description as the partition key. I specified group ID. So I'm going to give it, which is essentially the exact same query, only using the partition key, and run it. And when it comes back, I get the exact same results. But in this case, it's now down to 132. So we went from 175 to 132, which at large scale is a pretty big difference for optimizing. It's something called a single partition query, and it's the way that Cosmos can optimize because it doesn't have to jump over as much space on disk when it's querying. You can go into the portal and see how it's managing it. Even though it's fully managed by Cosmos DB, you can look under the hood. So here I'm seeing the distribution of data across partition keys. You want to try to keep these as close as possible. So you can see I have an outlier on one side a little high, one a little low, but most of them are pretty similar. These are the physical partitions that it's chosen to use. So it picked, for whatever reason, 5 physical partitions. Inside each of those, I can drill in and see that there's 3 logical partitions inside of each of the 5 physical. And that's the units it's going to use to replicate and shuffle data around. Now, to get to this point, let's take a look at some of the code involved. Let me pop out of here. So this one I wrote as a .NET Core project. So it's cross-platform. You can run it pretty much anywhere. What I'm showing you here is the connector that I share across projects. And notice that it's a Mongo connection settings. This is not a Cosmos DB SDK. Just using the out-of-the-box MongoDB, and I'm tricking it because it has no clue it's talking to Cosmos DB. That's why we created that API compatibility. I wrote a program to test once you import the items. Do we actually have a connection? We can run it from the console. And this does something pretty straightforward. It's getting a collection, and I'm telling it to type that collection as a food group. So this is the entity I want to cast it to. And I'm getting it as queryable. But if we look at as queryable, all we're doing is sending it to a list. So this is, again, straightforward code that we're familiar with every day, and it'll be similar with other APIs. We iterate through that list, and then I'm doing another query on food items, and this time I'm just getting the first food item, just to test that that's there. So if we run that, and again, so we're in the code base, we'll pull up our shell. I'm going to set some credentials because I'm pulling it from environment variables so I don't have to share it with everyone else. And then I go into that console test program, I run. Grabs the list of food groups, dumps those out, gets the first food item. So it's a really simple example just using a MongoDB driver. Now we can get more complex with this, and we can build a web API controller. That's what I have over here, that exposes it as an API that I talk to from, say, a single page application, Angular, React, Vue, one of those options. And again, the point that I'm stressing is I grab the collection, and then I'm using a straight link query syntax to grab the food items based on that code and pulling them back. So if we mix this all together and we come out with a batch of code, this is a Vue.js app that's also part of the open source project. And what I'm going to do is first I'm going to run the query that I showed you in the portal. So I'll pick dairy and egg products. I'll enter a search text. I'll say I want scrambled. We'll do a search. And we can tell that we are probably going to end up going to video here in a second. Okay, so it pulled them back. And if I click on the individual item, I get all the nutrients. Now this is actually good for me that I have a little bit of a slow connection, because I want to show you something else. I happen to follow a 100% plant-based diet, so I want to look at things like how can I get calcium or how can I get iron naturally in my diet. So I'm picking nut and seed products, and I'm going to pick, in this case, calcium. And what I want to do is if we grab calcium, I want to get the top food. So I want it to sort the top 100 foods in calcium by weight. So it's going to use that built-in index to do it. I didn't tell it to index these properties. It did them automatically. We're going to go ahead and click Get Top Foods and allow it to go out and grab that interface. And pretty quickly it came back, and I can use other nutrients, and we can see that the top item has a pretty good amount of calcium in one serving of that. So that's the implementation there. I want to show you one more implementation, and that's this concept called Gremlin DB. So this is a special language that's designed for querying graph databases. So I can get vertices, and I can ask for edges and nodes and connect across those. So if we look at the code snippet I have here, and I'm not going to go into GraphDB syntax, but I have an application that plots flight paths. And what it's going to do is it's going to take a from airport and a to airport, use this Gremlin syntax, and basically recursively look at all the connections that are possible to plot paths between endpoints. And this is, again, an open source project that you can take and run for yourself. This one happens to be written in .NET. And I have this posted to the web as a app service app. So what I'm going to do is take Seattle, which is my hometown, and plot paths to Sophia. And I'm going to click Submit. And what it's doing is it's posting to the server. It's taking these two endpoints, telling it to recursively traverse the edges of the points, come back and give me paths. And these are the options that I have between the two endpoints. And again, we're dealing with a little bit of a slow connection. So there should be like a green dot and a red dot for the front and back. There we go. And so I basically have a few choices of what I can connect through for that flight. If I take it to my former hometown, I move from the east coast of the US to the west coast, and I do a search for that, this is going to come back with a lot more connections. There's a lot of options for connecting through flights. We're going to let it pull that back and render it. And again, I know we're getting close to lunch, and the last thing I want to do is break into your lunch, so I'm going to go ahead and do the cursor thing. And if you have a tablet or a laptop up, you might want to do the cursor thing too. We need all the help we can get right here, apparently. And there we go. We've rendered. You can see lots of squiggly lines. The important one for me is that green one, which means a nonstop flight that I can sleep on and comfortably reach my destination. So I showed you several interfaces. For the interest of time, we're not going to dive into Cassandra, but I am showing a code snippet that this is the same philosophy. I can use Cassandra's driver, and it has no clue it's talking to Cosmos DB. This is meant for portability and compatibility. And I have this feature wall that I'm not going to spend 20 minutes going through, but this is meant to show your manager when they start asking you, well, what about security? Well, we hit these security check marks. What about a local emulator? What about geofencing? What about, there's a lot of features that are built into this. We could do a full day workshop and talk about the different nuances. Geofencing, for example, is interesting. If you have data in a protected country, it's going to keep that data there so that you can guarantee it's not going to leak and go somewhere else. So hopefully what I've shown you is that there's a different approach that you can use in addition to SQL. It's not better. It's a different set of tools for a different job. Azure is a solution that can handle a lot of those instances and flavors of NoSQL. It's .NET ready. I say that because I know there's a lot of .NET developers, but it's also JavaScript, Node.js, Python, Go. There's a lot of libraries out there that support this. And I threw in 42 because I did call this the Hitchhiker's Guide to the Cosmos DB, right? So having said that, thank you so much for coming out. Have a great lunch. These are links to the projects. I will post the deck. I will tweet out the link to the full deck so you can get all those links. Thank you so much for your time. I appreciate you.